Good afternoon, Greg. This is Anna in Derry, and today we'll present to you our breast cancer classification project. This is the final presentation in which we will briefly describe the project, explain the implementation using two algorithms, the adjustments done, and the results achieved. Breast cancer affects around 2 million women per year globally, and early prevention can save lives. So the scope of this project is to create a classifier using machine learning algorithms on an invasive ductal carcinoma dataset that can reliably identify a histological image as benign or malignant. I will talk now about the dataset used and the method of pre-processing. The dataset used to train and test the program on is the IDC regular dataset of histology images from Kegel. This dataset contains over 270,000 images obtained from 162 whole slide images of breast cancer samplings. For this project, malignant and benign values have been classified as 0 and 1, and the dataset that we used had already the label encoding implemented. Label encoder is an effective method used to convert text or categorical data into numerical data, which the model expects and performs better with. This approach basically just converts each value in a column to a number. The pre-processing done was to split the data into 80% for training, 10% for validation, and 10% for testing. Derry will explain next the implementation of the two algorithms used, all the adjustments done, and the results we got for each of them.
Okay, hi Greg. Yes, so we decided that we'd test out our proposed convolutional neural network against another algorithm model to see how they performed against each other and if our choice of CNN was good. With the logistical regression algorithm, it proved to be about 15% less accurate than the convolutional neural network at our baseline. So we pressed on with the convolutional neural network as the best for image classification in this case. We started out at 2 epochs because of computational speed, and we got a baseline on the Adam optimizer. And after that, we decided that we'd try all the other optimizers to see if there was one that performed better. Adam was the clear winner here, but Eta Delta was a close second, and we decided going forward that we would do our tests on both of these to see which would win out. We started off in the model with 3 layers, looking for features of a 3x3 size in them. We did decide to reduce the layers by 1 to see if it would reduce the speed or increase the speed of our training, or would it increase or decrease the accuracy. It didn't really affect the speed all that much, and it did decrease the accuracy a little bit, so we decided to stick with the 3 layers. As well as that, we decided to increase the feature size from a 3x3 to a 5x5. This vastly skewed the sensitivity and specificity. It reduced the accuracy as well, but the skew between the sensitivity and specificity was terrible. So we went back to the 3x3 feature. We increased the epochs up to 10. This was very computationally intensive as we were doing it locally on the CPU, but it did increase the accuracy by about 1 to 1.5%. Adam won out in the end because its accuracy was better, first of all, but its gap between the sensitivity and specificity was very good, whereas Eta Delta had a much greater gap of about 20%. It favored finding benign samples rather than malignant samples. It was much better at finding benign samples. So we decided we'd go with the Adam at the parameters that we'd mentioned as it had the best one. We had set a goal for ourselves of 90% accuracy, but we fell a little bit short, just under 87%, but it's a pretty good place to be. Okay, so thank you very much. Any questions? How do I stop?